Hi, and welcome to the third video in our 10-year anniversary series. This one is entitled Multi-Area ISIS, Ultimate Scaling for the Infinite Enterprise, and it's July 2021. I'm Ed Kohler, and I'll be your host for this session. So our agenda is going to be fairly straightforward. We're going to start with a concept overview, and then we're going to move on to one of the biggest benefits for ISIS multi-area, and that is something called secure service zoning. We're only going to touch on the surface because it can be a fairly detailed dialogue. I'm going to have another session later on in the series to cover it in more detail. But it's a big benefit and probably one of the biggest reasons of why you'd want to run ISAS multi-area. And the best part is you don't need to have a large network in order to do that. You could have as few as 50 nodes and still utilize ISAS multi-area and benefit from the concepts of secure service zoning. So it's worth spending a little bit of time to go over. We're going to then move into some good to know facts before we move into design concepts. Once we have that under our belt and we have a good foundation, we'll start to move towards migration concepts and scenarios. And then we'll wrap up with fabric edge and multi-area and how the two work together to provide the best of both worlds. So SPB multi-area is a new release feature in VOSS 8.4. And there are really three main reasons that you want to interconnect multiple ISIS areas. The top bullet speaks to one of the big aspects, and that is for network scaling. As most folks who have Fabric Connect installed today, we realize it's limited to around 1,000 nodes. Many of our customers go beyond that number. Now, to people that only have 2 or 3 nodes, you might say, well, this isn't a big thing. However, there are some features here that will benefit you regardless of the size of your network. Number one is multi-area provides route summarization for both the GRT and the L3 VSNs between areas. That's a big benefit. That cuts down on a lot of traffic, a lot of chatter. It actually provides the ability to interconnect also smaller interior gateway protocol domains. So when you look at the two benefits of route summarization and the breaking up of smaller IGP domains, we reduce the CPU load. And this is particularly beneficial on smaller devices, particularly edge type devices or smaller branch type devices, things of that nature. It also becomes very attractive to break up areas, for instance, WAN versus the actual campus environment, things of that nature. So there are some really big benefits that you can realize. But when we're on the subject of scaling, we recommend that you take a single area and keep it about 500 nodes at a max. That's not a hard number. You can exceed it. Just keep it around 500. Now, as I said earlier, you can have much smaller areas. You can have 20 or 30 nodes in an area. This is just the maximum. Now, if we keep to these rules, we can have a multi-area fabric that can scale to tens of thousands of nodes. And this is in a single end-to-end fabric. That's a very powerful thing. Now, in addition to the route summarization and the interconnection of the smaller IGP domains, we also have this feature in the middle called secure service zoning. As I said earlier, this is probably one of the major benefits of SPB multi-area in my mind as a security person, because services can span anywhere within an area and or across boundaries. So you can have an ISID go anywhere within the network if you wish. However, it also provides the ability and option to restrict ISIDs from crossing the area boundary. A great example is a data center where you're saying, hey, I don't want any of my ISIDs to leave my data center. Anything that happens, I want to happen through the security demarcations. So now it's important to realize that this is the default. If you took multi-area and created a data center area, it by default would share nothing. It's all ISIDs will be restricted, but you would be able to go in and actually share services. And this is an important thing that we'll talk about later on. This is a good slide for the concept overview. It's important to realize that everything happens in what we refer to as area boundary nodes. And a couple things, obviously, is they need to run VOSS 8.4, but they also need to be VSP 7400s, and they can either be 48Y or 32C. Provided you meet these two requisites, VSP 7400s and VOSS 8.4 running on them, they can become area boundary nodes. All of the magic happens in the area boundary node, and it'll be obvious in the next slide. But it's important to realize that this provides the actual functional boundary, and then you can see we have a series of colors for the links interconnecting the switches. Before we go into that, I want to talk about the colors of the other two switches. You'll notice that in 49C1, we have regular purple switches, and then 49DC1, we have regular purple switches down there as well. They are normal SPB nodes. They view their area just like they've always viewed the area, and in 49DC1, they would view the area boundary nodes is a valid node within the area 49DC1. So they see nothing unusual here. Same thing in the home area up at top. Now, this will become a little bit more obvious. It's a little bit more complex than that. We'll talk about the details on that. But it's important to note that the nodes that are resident in each area can be running any version of VOSS. They could be any model. The only requisite is that the boundary nodes themselves have to be VSP 7400s, and they have to be running VOSS 8.4. A little bit more detail on the color of the links. The red color, and this will be consistent throughout the rest of the session, represent normal home NNIs. So these are NNIs that are fully resident to 49C1. Same thing down below. We see a red line between these two switches. That's an NNI that's fully resident within 49DC1. You will see that we have yellow links. Well, those are remote area links, and this is really where the magic happens. The remote area links are important because they actually present themselves, or the node, and we'll talk about that, to the area, and it basically, for all intents and purposes, is part of 49DC1. So we can have normal code running here in normal SPB nodes, and this provides a very modular way to introduce multi-area. Now, another point here is you'll see a third color. There is a green color. This basically is an NNI link as well between the two area boundary nodes. And note that it is both a home and a remote area link, and this is for purposes of resiliency and also traffic optimization. Now, by default, there is no redistribution. So once you set up multi-area and you have these two areas interconnected, none of the services will be visible on each side. And that is by default. We need to go in and do service redistribution, and that'll be what we'll talk about with secure service zoning. And you could do it for L2 VSNs and E-trees, GRT and L3 VSNs, bridged and routed multicast, DVR backbone routes for data center area interconnects, and then also ISID mirroring, which is kind of neat as well. This is a little bit closer look at an area boundary node. So from the northbound side, we can see that we have our red links coming in. Those are NNIs. Those are the home area NNIs. We can also see that we have user to network interfaces that are interconnected. And it's important to note that any UNI ports on the area boundary node, as well as internal IP interfaces, DVR controller, if you are running it, or nickname server, if you're running Zero Touch Fabric, they all belong to the home area, not the remote. Okay, so that's an important thing to realize. Now, as we move down below, we see a redistribution function, and we can also see that this is where the boundary is between the two areas, 49C1 and 49DC1. Now, the remote area links are the links that attach into the nodes into the remote area, and the redistribution function is where we would actually set up the lists to extend or restrict traffic. Again, traffic is restricted by default. There is no redistribution. This is a look at secure service zoning, and this is probably one of the most powerful aspects of ISIS multi-area, at least from my perspective, being a security guy. I'm not going to go into a lot of detail. I'm going to have a separate session on this, but we'll just go through a little bit on these case points. Pretty simple. We look at a multi-area type policy, create an ISID list. In the L2 scenario, we scope out ISIDs 1 to 80, and then we create a redistribute, and then we deny all, accept the list, and basically we're sharing ISIDs 1 to 80 outside the area. Everything else will be restricted. Same thing, and then a unicast, create our route map and so forth, so on. Very similar to the route redistribution. At this point, though, you'll notice that we're doing a home to remote, but we can also do a remote to home as well. And this is an important piece, but not much outside of what you do in a normal type of route redistribution policy. You can see that L3 multicast, that is a little unique now because this is new. We're providing the ability for leakage of multicast routes between the areas. Now keep in mind that multicast would be, like every other service, restricted to the area. So if you want to have certain IP multicast groups that are extended out to other areas, this is basically the type of listing and zoning that you would use. And then finally, down below, the last bullet, we see multi-area DVR redistribute, and that's basically where you have, say, two adjacent areas, and maybe you have data centers, and you want them to actually share routes. This is basically how you would accomplish that. As always, before we go into design concepts, it's always good to go over a few good to know facts. First thing to realize is ISIS multi-area uses two equal L1 areas. And that's an important thing. They're simply peered L1 areas, and the area border nodes accomplish that peering. Connected areas will appear as virtual nodes, and the actual diagram here shows that. We have BG1 and BG2. These are our actual physical area border nodes, but we can also see that they share virtual nodes that are created by their relationship and the fact that they're area border nodes. And we can see that one virtual node is labeled VB and the other one is labeled VG. This is because they act as proxy representations for their areas. So VB acts as a proxy representation for 490050. You could have hundreds of nodes in this area, and it's all represented in the VB virtual node. Same thing conversely. VG is a member of the blue domain. He's a full member of 49000, but it's a representation of 490030 as far as LSDB, LSP information. And again, there could be hundreds of nodes within this area as well. So this boils down to a rule where connected areas basically count as one additional node each. That actually is a very, very big benefit when you think about scaling. And then we have to add in the one or two boundary nodes as well for the home area. Now, the big thing here is that all traffic is destined to the virtual nodes. And they show up, they look just like normal nodes, and we'll have some further detail on that. Obviously, two area boundary nodes can share a virtual node. There's an election process that takes place as far as who manages it and handles it. Redistribution policies on both boundary nodes need to be the same here. So as we look at this diagram with BG1 and BG2, any of the secure zoning that we did, we really have to make sure that they match. Now, in the lower diagram, we can see reference to some of the lower bullets below. First of all, area topologies need to be built loop-free. That's an important design concept, so it's a good-to-know thing off the bat. So in the example here, we have three areas, and they're kind of ringed together. The node between area blue and area yellow will not come up because that's going to protect. So you don't have a ring, you have a chain. You have a chain of three that touches down to the lower bullet where don't chain more than 5 areas. So you could see if you kept on with this design practice of building a ring of areas, you would reach a chain of 5 fairly quick. So that's a big part of design practice to remember. And then the other thing to remember is if you're running zero-touch fabric, the seeds in the nickname servers, they need to be created per area. So you'd have a ZTF domain in 490030 and another one in 490050. Let's talk a little bit more about virtual nodes because they're obviously very important to this concept here. We see a number of areas here and we're identifying the area boundary nodes in purple. We're going to use this as a case point example to explain some of the activities and the roles that the virtual nodes provide. Now, it's important to realize that the nodes shown in green, they're all regular BEBs, BCBs. I said that earlier. They can be any version of VOSS. They can be any model switch. It doesn't matter. All of the magic happens within BG1, BG2. Now, the important thing to realize about a virtual node is it's representing an entire complex topology, and it's summed up in the single virtual node itself. And that happens by the inter-area exchanges that are occurring. And we'll talk about the details of how this happens. In this case, for area green, VB will represent the services from area blue, orange, and yellow. So this gets to the concept of representing entire areas or trees of areas, if you will. And as we start getting into some of the design concepts, you'll start to see this being realized. Now, it's important to realize that virtual nodes are seen and treated just like any other physical node. Now, it's important to realize that in the case of two area border nodes that are sharing a virtual node, one boundary node is elected as the active boundary node, and that active node, physical node, will handle all LSP for the virtual node. So let's say BG1 is elected as the active, and that happens by the lowest BMAX. So let's say BG1 has the lowest BMAX. It is elected as active. It will handle all of the LSP information for VB. And if BG1 were to fail, BG2 would take over. Now, I want to emphasize this is only for the LSP. This is not for normal traffic between the areas. All NNIs on the physical nodes are functioning and moving traffic. This is just for the handling of the LSP for the virtual node. It's important to realize that just like a regular SPB area, each SPB node has its own perspective. It's the same thing with areas. So if you got that concept, then it's very easy to jump to this. So each area has its own perspective, and each adjacent area is represented as a virtual node. So this builds a structure of physical and virtual nodes, which are obviously the ABNs and then the virtual nodes themselves, representing more distant areas. And they're all hiding between each virtual node. So when we look at this, area yellow will not only see virtual node blue, representing area blue, but it will also see other areas further beyond it. The other thing that we've done to make this easy is that we've automated as much as possible the virtual node and its creation, the nickname assignment, the system ID, the host name. We make that as automatic as possible. Now, I want to emphasize that you can go in. There are commands in the CLI for you to actually be very specific in the way you want to have these deployed, but it's not necessary. We basically derive it from the last 5 nibbles of the manual area, and then we go from there. And it's a pretty rock solid way to move forward. We kind of suggest that you would keep this as your default behavior. However, you can go in and actually manually indicate what you want these values to be. So now that we have the good to knows done, let's talk about some of the multi-area design concepts. There are really multiple ways we can go about this. We can do the direct interconnect. That's what we've been talking about up till now. And that's basically where the area boundary node creates some remote NNIs, and they link down into the remote area, in this case 49DC1. You can see that we're reusing the same example. And those are presented by the virtual node as a valid member in 49DC1, and these nodes see nothing different. They're just regular VOSS nodes, and they're running any version of VOSS, any model of switch, so forth, so on. This is one method. Typically, as you move beyond 2, you're going to want to create more of an architecture, and we can do this through the use of a backbone transit area. And these can be of 2 natures. They can be passive, as in this case, where the backbone transit has no switches, or they can be active. So you can have an active core. We'll talk about that later on in the design. Now, what makes this environment? Well, as you can see, you'll notice that we not only have area boundary nodes up at the top in 49C1, we also have area boundary nodes down below in 49DC1, and this creates a backbone transit area, 49BB. So this becomes particularly important when you want to scale out to multiple areas, perhaps 4, 5, 6, maybe even beyond that. This is where backbone transit area becomes a very important design concept. Note how in each of the examples we're showing the green link between the area border nodes. That's important to realize that those are both the home and the remote. The other example on the far side is a transit area that's with using fabric extend. So remember, an NNI is an NNI. It really doesn't make a difference. So we can run and create a transit area with fabric extend. The only technical note is that a virtual port cannot be part of the remote area in the home area. So in the case where you're using Fabric Extend on both sides, you will need to be sure that you're using separate virtual ports. It's not often that it would come up, but do realize that that is the case. So now let's introduce the concept of the transit area and how we would accomplish it. So step one, we configure the boundary node functions. Then we create our new area. We set up our area boundary nodes. We interconnect them, and that basically is what allows us to create the backbone transit area. And there are multiple ways we can deploy this. We can do a mesh type of deployment. That's in the direct links far left side. We can also do a ring type of backbone area where you can see that the NNIs kind of follow in a ring formation around. Again, these are all direct links. And then again, as I talked about earlier, we can talk about an active transit network. So in this case, we have actual core nodes that provide an active backbone area. All of these are valid. You might say that one might be evolutionary towards another, but they're really not. You could deploy and move forward and scale quite large with any of these deployment areas. Do note, though, as I said, that the green links are part of the home and the remote area. And then also realize that we do have our loop protection. So if you, for instance, tried to create an adjacency in the middle example, it won't come up because it's going to indicate that it is a loop. So now let's talk about migrating to a new ISIS area. In this example, we have an MLAG scenario, and we have a single area. What we want to do is we want to break out to multi-area, and we want to kind of move over to a fabric to the edge. So let's see how we'd accomplish that. We start out by creating a new area and creating our SPB boundary nodes, and then attaching them back to the original area. Note how we're attaching down to the bottom switches, which would be actually probably the data center environment. And then up on the top, we are interconnecting over to the actual distribution closet. So these boundary nodes would then exist. We would then be able to start to pull services. So in this example, we're taking this stack and decommissioning it, and then we're bringing up Fabric to the edge and equivalent to it. And basically, at that point, we would be able to remove and move from an MLAG to the new area. And then eventually we move to the concept of where we have a totally separate area network interconnecting down to the data center. And now the area border nodes provide two separate areas in this infrastructure and a complete conversion over to Fabric Attach Edge. So you can see that these are all Fabric Connect nodes now, and we're running Fabric Attach supporting our wireless APs, any switches that we needed, or anything else that we're running Fabric Attach as a protocol to the edge. This is a case of where we have Fabric Edge, and this is a great example of if you had a very large network, let's say area 4900, and you were getting close to 1,000, and you said, you know, I really want to break this up. Well, this is basically same type of process, really basically. You would create a new area. You would take that new area, the area boundary nodes, and you'd attach them back into the original area. At that point, you'd start to move the fabric nodes over, NNIs down to the area boundary node, and you'd move, let's say, for instance, you'd move half. Okay, so let's say you were at 800 nodes, so you took and moved 400 and you put them in 49C1, and then 400 remain in 49DC1. And that's basically how you take a very large SPB network and then start breaking it up into multi-area. This is a very handy approach, and it works quite effectively. And as you can see, it works not only for FA Edge and MLAG, the whole approach is consistent across the board. So this brings us to the concept of an actual multi-area blueprint concept, because it's important that we want to maintain our limit within the chain of 5, and we want to make sure we have no loops. We want to make sure that we're able to scale and not exceed any of the topology rules. And as you can see, they're fairly generous, but they're important. It's important to be cognizant of this. So in this case, we have a fairly large network as an example, and we can see that our area backbone is passive, and we have several areas that are kind of function-based. We see that we have area 1, which has DVR, and it actually has regular BEBs. So this is a fairly normal type of scenario. And area 1 is interconnected into the backbone area. Area 2 is DVR only. And we also have area 3 and area 4, and they're kind of mixed, particularly area 4. This is mixed migration. This is basically where we're perhaps running route redistribution out to external networks. Here we see a PIM gateway, things of that nature. But it's important to realize that our area boundary nodes also have this shared green link. Again, this is our home and remote areas, and you can see that's consistent across the board. And down below, we see our data center. This is where we probably restrict a lot of the ISIDs, and we wouldn't allow that. We probably say the only way that any of these other areas can get to this is through security demarcation. On the other hand, there may be certain services that we want to extend out of the DC domain into specific other areas. And here we can see that we have a very large scale topology. And we can see that we've developed the concept of a WAN backbone area. And you could envision this as a massive active core that could cover a vast geographic area. Imagine a county or a state or something of that nature. And then we can see that we have metro areas that are there, and then areas that are broken off of that. And if you do a count, you can see that we're within the chain of 5 in any instance. This is a very good design, and you could get a vast amount of scaling here and never exceed the chain of 5 rule. So here we would definitely benefit from the aspects of secure service zoning. Imagine if these were multiple agencies in a government or multiple tenants or things of that nature. This is a very, very important thing to realize. So it's not just the scale. Realize that we could utilize secure service zoning in each of these scenarios within the end-to-end topology. Very, very strong benefit from a security perspective. And finally, let's wrap up with VSP Edge and multi-area. There are a lot of benefits of why you'd want to marry the two. In this example, we see 3 areas that we've created, and then we have a 4th area that is our backbone transit. Again, this is a very good design. If you're going to move to more than 2, then you really have to develop the concept of a transit area. And here we can see that we're moving to a transit area, and then we're moving up to campus 1 and campus 2, each with separate DVR domains. Now, these DVR domains are DVR edge domains. So we have DVR leafs. They're all going out to support the users within the campus environments. We can see that they're interconnected down through the backbone transit area to an area boundary node that feeds into and is top of spine to the data center environment. And we can also see that this is where our connection to our management infrastructure would be, our XIQSE, our DHCP and radius. And we can also see that this is where our management environment would come in as well. So this becomes very, very key. And the other thing to realize is the connection to the management segment could be bridged or routed. So here we have global services for the whole end-to-end fabric. That's XIQ, XIQSE. Our radius services, our DHCP services, our DVR backbones, the ISID ranges, those are all global and restricted by default, but ISID ranges, secure service zoning, could extend ISIDs anywhere within this end-to-end framework. And then we have network services that are specific per ISIS area, and that is our nickname servers, as we talked about earlier, and also our DVR controllers. So I hope that gives you a very good view of the innovation that we provided with multi-area ISIS, not only its capabilities for scale, but its capabilities for extremely granular service attributes within the fabric itself. Thanks a lot for your time. I'm Ed Kohler, signing out.